Thank you, Dr. Ananthasanam. This is the joint work with John Lewis, my colleague. He has been at the National Severe Storms Lab as well as Desert Research Institute in Reno, Nevada. How does it go down? Which one? Could you tell me? Yeah. So some of you may have heard this, so you can take it easy. This is a paper that was published in 2010. I'm going to present the theory. We have applied since then to a couple of different problems, one with respect to estimation of parameters and initial conditions in a class of carbon cycle models in ecology. Also, another class of model that is of interest in civil engineering. When there is a big storm like Katrina comes in, there's a huge surge, and they would like to be able to predict the amount of water that comes along, and it's an extension of the shallow water model. They have parameterized that model in specific ways. One PhD student used this method to be able to estimate parameters. I'm not going to show you any of the applications. I'm simply going to be content with talking about the theoretical underpinnings of the forward sensitivity method. If anyone is interested, I'll be delighted to send you the reports later. Models of abstractions of reality. Observations are samplings from the true state. The goodness of the model is judged by the ability to explain observations. The difference between the observation and the forecast is generally called the forecast error. The use of inadequate or defective mathematical models, for example, subgrid processes, generally are not captured by the models. The wrong values of the control. The control could be initial condition, boundary condition, parameters. The function h that maps the observations to the model state space could also not fully capture what's going on. Observations are corrupted by unobservable measurement errors. In fact, we can have combinations of all these things. Some of these errors are more tractable than others, and these errors are really the cause for some of the challenges that we face in data assimilation. Thanks to modelers, great strides have been made in the development of good acceptable models. We are going to assume the models are perfect. It's also assumed that the relation H between the model state and the observables are well known, well tested, and they are good, acceptable. So given this premise of knowing H as well as good model, the forecast errors can largely be attributed to errors in the control, namely initial condition, boundary conditions, parameters, as well as observational errors. These are some of the easily tractable version of the problem. So we posit that the forecast errors can be divided into two parts, the deterministic part and the random part. The deterministic part is called the forecast error, or the bias in the forecast. The random errors are induced by the random measurements errors. Our aim is to be able to isolate the deterministic part of the forecast errors. We all know much of this. Models are representations of reality. They are coupled to nonlinear partial differential equations. These are infinite dimensional models. They can be made more conveniently for numerical work, either by spectral methods, by Galerkin type projections, or by using finite difference approximations. Within the framework, our framework has been adapted to cover both the discrete time finite difference equations as well as ODE kind. I'm only going to describe the one that applies to finite difference equations. For more extended ones, I have copies of report I can give you. So quickly, t is the time, x is the state, alpha is the parameter, f is the model map, x dot is equal to f defines the model, x naught is the initial condition, alpha is the parameter. We are going to assume f satisfies all the usual conditions necessary for the existence and uniqueness of solutions. The solution x of t is in fact a function of initial condition and parameter, I'm going to assume that f satisfies all the required conditions to render x of t to be continuously differentiable with respect to the initial conditions as well as parameters. So we are going to call the product space initial condition, which is Rn. This is Rp, the product space, as the control space. So H is the map. Let us assume x star is the actual true state. The observation is equal to the truth plus the noise. Oftentimes x star is unknown. V is the unobservable measurement noise. I'm going to assume V has zero mean and the known covariance matrix. And I'm going to assume that R has nice properties, namely it is positive definite. So if I know the model state, I can predict the observation. This is the model counterpart of the observation. This is the actual observation. The difference between the actual observation and the model counterpart is the error. This is also the innovation, the new information that the observation brings to the table, in addition to what the model tells us as to what the observation ought to be. Recall z of t is equal to h of x star plus vt. So if I substitute this, I can readily get the error, which is the innovation. If you substitute this, I can isolate the deterministic part, that is the random part. The deterministic part is essentially the difference between h of x star plus minus h of x. The deterministic part is called the forecast bias, and that's exactly I would like to be able to correct. And we all know that one of the ways of correcting this error is to be able to change x of t. X of t is the model solution, and the only control we have here is to be able to change the control parameters, which are initial conditions and our parameters, because we assume the model is perfect and everything else. So I would like to be able to quickly run through, if the model is perfect, the initial condition, boundary conditions are all known exactly. The actual model state is equal to the truth. In that case, Vt is 0, Et is equal to Vt. In other words, the error in the forecast has a mean 0, it is normally distributed. If the model is perfect, but there are errors in the initial conditions and boundary conditions, then the forecast error has a non-zero deterministic part and a random part. The non-zero deterministic part essentially arises because of the difference in the initial condition and boundary condition. The third is a more difficult case. In this case, in case 2, I'm expanding this. BFT is a function of C, which is the control, as well as the time. And in this case, the average error must be equal to the bias. Case 3. You suppose if F is an error, H is an error. It's time for me to stop. Okay, so EFT is equal to BFT plus VFT. In this case, BFT, the bias is a function of the model error, observation error, control error. So this is the complex structure. This is the most difficult thing. This is what happens in practice. And this is one of the more difficult cases to handle. Because it is more difficult to handle, for case 1 is trivial, we are going to take the intermediate case of case 2. So what is the assumption of case 2? Model, I'm going to assume, is a good model. The observation operator is a good one. And so any forecast error can be attributed largely due to errors in control. Okay, that's exactly what I have. Okay, so what is the idea here? Find the corrections or perturbations to the initial conditions and the parameters such that I can annihilate this deterministic part of the forecast error. That's the way we are going to state the problem. So this is the pictorial view. I started with the initial condition and the parameter. I make a forecast. This is the model forecast conditioned on this. This is the model counterpart of the observation. If that is the model counterpart of the observation, the actual observation is Z of t. Z of t minus Zm of t is the actual error. I would like to be able to annihilate that error. So this is the error, Z of t minus Z of t f m. The way I'm going to do it is to be able to perturb the initial condition and the parameter simultaneously. This is the new initial condition, this is the new parameter value. I'm going to compute the perturbed state. The perturbed state is yt. I would like yt be such that zft, the actual observation, if I put this yft through the model parameter, h of yft matches zft much better than h of xft did. So the whole question is this: in order to make this happen, what must be the value of delta x not delta alpha? That's the question I would like to be able to show. So formally, how do I pick the perturbation such that EFT is going to be close to 0? EFT is going to be close to 0. So now I'm going to describe this variation quickly. Xt is the model forecast, C is the unperturbed control, delta x naught, delta alpha are the perturbations in here. So if this is the new initial condition, new parameter value. This is the first variation. So let delta x of t be the first variation of the solution induced by the perturbations in here. So going back to the previous slide. So what is it I'm interested in? Given, I would like to be able to express this in terms of these quantities. In the conventional 4D-WAR, this is done through what's called the tangent linear model. Now I'm going to relate these two using what's called forward sensitivity relation. That's the difference. So the method is a close cousin of 4D-WAR, but comes from a slightly different angle. So let delta x of t be the variation. So h of x of t is the original model counterpart. So if I perturb this, my h function induces delta h. So h of y of t must be equal to h of x of t plus delta h. To be able to see that pictorially, I would like to be able to go back in here. So this should be such that when I plug this, so this y of t is equal to x of t plus delta x of t, use the first order Taylor series expansion. So z of t will be equal to the model old prediction plus the correction. The correction from here, you can see I have to match that correction induced on delta h to my error. So these two equations becomes the defining equations for my analysis. So this is another way of looking at it. I think I already talked about this. I would like to be able to the model to match the observation. This is the truth. This is coming from y of t. Y of t is equal to x of t plus delta h. So if you substitute, do the little bit of an algebra, you simply get E of t is equal to delta h. So what is delta h? It is the increment in the model predicted part of the observation induced by the perturbations. And that's the first variation. I could do second variation. We have done all those things, but for simplicity, I'm going to do only the first order analysis right now. Okay. Now, I would like to be able to relate delta h with delta t. So you know the h function. So from basic calculus, we can see the first variation in h is equal to the Jacobian of h with respect to x times delta x. This is the Jacobian matrix. We all know the Jacobian matrix is a m by n matrix because the observation space is m dimensional, the state space is n dimensional. And now comes the idea in here. So let me go back a couple of steps so to be able to relate that. Sorry. So my aim is to be able to compute this based on this. I'm simultaneously changing the initial condition and the parameter. So to compute this, again, I'm going to go back to the variational formulation. The change in the model solution at time t is equal to the Jacobian of x of t with respect to x naught. That is given in here. So what is this? I would like you to look at this matrix. This is the model's first component of the model solution at time t. This is the first component of the initial condition at time 0. So I'm trying to compute the derivative of the solution at this time with respect to the initial condition. So this matrix is called the forward sensitivity function. I'm talking about the sensitivity of the model solution at time t with respect to the initial condition. So that's the forward sensitivity. It's a first order sensitivity. Likewise, I have the sensitivity of the model solution with respect to the parameters. So this is the model sensitivity, model solution sensitivity to parameters, model solution sensitivity with respect to the initial condition. If I know these two, and these two can be easily computed, how I will show you in a minute. So if I know this matrix, basic calculus tells you this times x naught plus this times delta alpha would be that. So I have now related everything back to delta x naught and delta alpha. I'm going to put it all together now. So delta h is equal to, in other words, delta h is equal to d of h. So if you substitute all the things, you quickly get an expression. I don't want to belabor the issue of trying to explain the arithmetic. Ultimately, what it boils down to is as follows. EFT, what is EFT? EFT is the vector that relates to the forecast error at time t. This is a M vector. This lies in the observation space. What is beta? Beta is a super vector. It's a collection of the perturbations in initial conditions and the perturbations in parameters. This is the n vector, this is the p vector, so this is the n by n plus p vector. And what is h? H is a matrix. H is a matrix. It is partitioned to H1 and H2. H1 is the product of the Jacobian of H with respect to x and the sensitivity of the solution with respect to x naught. H2 is again the product of the Jacobian of x with respect to x and the sensitivity of x with respect to alpha. We saw all these quantities a minute ago. So this matrix is a humongous matrix. It is a m by n plus p. So m by n plus p by 1, this is m. So this is a linear relation. This essentially tells you, this is the perturbation in the control. Beta is the perturbations in the control. It tells you how the perturbations in the control should be related to the forecast error through H. So we have already seen this is a linear least square formulation. So I should be able to find my beta by solving the linear least square problems. In this case, depending on the values of m, n, and p, it could be an overdetermined problem, it could be an underdetermined problem. Only for the sake of simplicity, I assume the observations are one time. If I have observations at various instants in time, what is that I could do? At each time, I have an equation of this type. All these equations are fairly independent, so I can stack them all together. So what does this mean? If I have k number of observations, I have k sets of these equations, one for each time instant at which I'll have observations. So I'll have a huge, humongous linear least square problem. That linear least square problem can be readily solved using standard methods which we have seen last week. So that is the expression for the solution. You can see this in chapter 5. Well, this is a technical matter. So I am able to now characterize my BFT. EFT is equal to BFT plus that. My solution BFT is given by this. If I took the expectation of this, the expectation of that 0, so I'm going to be able to get the forecast bias and relate it to the corrections in the control. We have applied this to a couple of different problems, but I would like to go back to the sensitivity equations. So the whole question now is that how do you compute the sensitivity? This is an alternative to the tangent linear models. So what do? We do the following. So we all remember this is the ODE formulation. X dot is equal to f of x of alpha of t. So I would like to be able to compute the sensitivity of the model solution with respect to the parameters. So what do? I take the differential coefficient of both sides with respect to alpha. Please remember, x dot is a vector, alpha is a vector. So this is the matrix of derivatives. And this derivative, del alpha of x dot, I can commute under suitable assumptions and smoothness conditions, and that is equal to dx by d alpha. And I can compute the partial of f with respect to alpha. I would like you to remember two things. X as a solution depends on alpha. F also depends on alpha explicitly. So the right hand side will depend on two factors. That is the Jacobian of f with respect to x times the Jacobian of x with respect to alpha plus the Jacobian of f with respect to alpha. So the sensitivity equation becomes d by dt of the model Jacobian, the Jacobian of the solution at time t is equal to model Jacobian times, look at this now, these two factors are the same, this is the matrix, this is the matrix, that's the matrix, that's the matrix. So what is the initial condition? The initial condition is independent of the parameters, so the initial conditions for this matrix is that it is 0. This is the first order differential equation, that's the forcing term. If you look at this, it is very similar to the tangent linear model. Those of you who remember the tangent linear model we derived for the first order adjoint method, there also the model Jacobian comes into play. But in here, I'm trying to, so what is this? This tells you the dynamics of evolution of the forward sensitivity of the model solution with respect to the parameters. Likewise, I can similarly differentiate the previous equation. I'm sorry. I think oops. Press the wrong one. Forgive me, please. Yeah. That's right. I differentiated this with alpha, now differentiate this with x naught. If you did that, you get this. Again, a simple exercise in multivariate calculus. You get another first order equation. In this case, there is no forcing. In this case, the initial conditions is an identity matrix. So once we have a characterization of all these three quantities, I'm now going to tell the steps. This is the model solution. So compute the solution for the model forward in time. If you compute the solution of the model forward in time, you can compute the Jacobian. If you compute the Jacobian, then you can set up these two equations. These are the initial conditions for the three equations. You can solve them by fourth order Rangakata method. You can compute the forward sensitivity with respect to initial condition, forward sensitivity with respect to parameters. Once these two and the H functions are known, I have the ability to construct my matrix H by the methodology we just described a few minutes ago. So I know the right hand side, I know the parameter H matrix. All I need to do is to be able to simply solve the least square method. This method can be, okay, we all know how the solution comes in. So we can use one of several techniques that we have talked about. SVD, QR decomposition, conjugate gradient methods. A family of different techniques could be used to be able to solve this. So this is another summary of the framework. This is simply a repeat of what I said. But here, what is the difference? The difference is that if I have multiple observations, I have one equation for one time, another equation for another time, another equation for another time. What is the only thing that changes? When n is 1, I have one observation. When there are capital N observation, this matrix becomes a little bit humongous. This is very close cousin of 4D-WAR. Am I almost done? Okay, I won't keep you for too long. It can be shown that this method is a very close relative of 4D-WAR. I'm not going to show that. Well, let me stop here. So in summary, what is the idea here? In the 4D-WAR, you compute the gradient of an objective function with respect to the initial condition parameters and use it in a minimum seeking method. In here, we directly compute the increment itself. So what is it we can do? You start with the initial guess, compute the increment, make the increment, iterate it. It can be used as second order approximations. Second order approximations are more accurate when the model dynamics is highly nonlinear. First order approximations are pretty good when the model dynamics is not too nonlinear. So we have situations where first order method doesn't give good result, but second order method does. Various modifications thereof, but I'm not going to go into detail. I'll be delighted to talk to you one-on-one. Thank you very much for your patient listening.
Random variable, then I am interested how the error propagates, because in a nonlinear modular if it is occurring.
Yeah, but that is not the problem here. The problem is that I have observations, I have model. I would like to force the model behavior towards the observation. My job is to find an appropriate initial condition. I'm not given one. So that is the difference.
Any other questions? Okay, if not, let's thank all the speakers today, and see you tomorrow at 9:30.